Okay, so let me first just show you what I have on the screen. Let me show you what I have on the display. And then we'll look over where we are currently in the course. So you'll see that I've mainly kept the lectures, these visualizer scan lecture summaries updated, and I've been slowing down the pace a little bit. So I still have to put up lecture 28. You'll notice that it goes up on Panopto as soon as possible, so that's usually about a day afterwards. And it's also on YouTube, but I have to link it into the individual website. So you can see, for instance, lecture 27, it's now been linked in, but I have to link in the other videos. It takes me about a day to download everything to my desktop and then upload them into Panopto, then upload them into YouTube, and then link them here. But I will get that done. So we're now in lecture 29. This is not quite so we're sort of going well into Easter, so I haven't quite decided how high up we'll go. The problem set solutions have been released up to problem set number 9, and then problem set number 10 is that last topic on the uniqueness of solutions. Okay. Also, keep an eye on the errata. So this is the website that keeps track of problem set typos, or typos in the lecture notes, or typos in the solutions, etc. So you'll notice, for instance, today I put in this problem set number 9, question 2 typo, which I found about a missing factor of p before I was doing the preparation for this lecture. In fact, this problem set number 9, question 2 typo, I remember that when we were still in session at the university, someone had pointed it out to me after one of the lectures, and I forgot to mark it down there, and I forgot their name as well. So if you were the person that pointed it out weeks ago, thank you very much. Okay, where are we in relation to the problem set questions? So there are 10 sets in this course. We're now well on our way through problem set number 9. So you'll notice that we did do problem set 9, question 1, during one of the last 2 weeks of lectures. We're going to have a look at question number 2 today. And this question is not too difficult. This is the case of a plucked string. But though we did the case of a plucked string where the string is plucked at the midpoint of the string, at halfway between at L over 2 if the string is length L. This is for a plucked string at a generic point P. So the basic techniques are all the same, but the integration of the initial condition gets a bit harder. Finally, the last 2 questions from this problem set, questions 3 and question 4, relate to this new material from chapter 18, which we hope to get a start on today. This is called D'Alembert solution. And rather than applications to study the wave equation, this is the wave equation here, on a finite string, so this is from 0 to L, the wave problems that you do in questions 3 and 4, and hence chapter 18, are about the wave equation on an infinite domain from minus infinity to positive infinity. Or you might think of that as a very long string. Okay? Where are we in terms of the lecture notes? So these are the typeset notes. And as someone had asked right before we started what to do about chapter 17, this is Laplace's equation using separation of variables. And I mentioned that you should know enough to do problem set 8, the very last question, the question that we just looked at last lecture. So this question here, which is Laplace's equation on a disk. But I don't expect for you to know chapter 17, this portion of that chapter, 17.1, about solving Laplace's equation on a box. Okay, so this is solving the Laplacian of u is equal to 0 in this rectangular or square domain. And that's essentially what the whole chapter is about. It talks roughly about this inhomogeneous problem, but still on the square domain. So you don't really have to read this chapter unless you're very interested. And if you do have a moment of time, then it's just good to skim at least the first page and to know what it's all about. But this will also be mentioned on the study guide that I hope to publish at some point, and it'll just confirm for you that you don't have to know chapter 17. And then we're going to get started with chapter 18. And chapter 18 is actually a fairly short chapter, but it shows you the very important technique and a very important formula that you have to know. Okay, so let's get started. We're gonna start now with problem set number 9, and then this question here about the plucked string. Let's read it over together. You have that the ends of a string, one at 0 and one at L, of a flexible string are fixed with 0 displacement. So the displacement u, if you like, is 0 and at 0 and L. And then at some point P, which lies within the domain from 0 to L, the string is drawn to a distance of h, and at t is equal to 0, the string is released from rest. So the initial displacement is given by this condition where the string is drawn to a distance h, and the initial velocity is 0. The string starts from rest. So this is your initial condition. You have a condition on the string from 0 to p, and then from p to L. And then you have the initial velocity being equal to 0. And the question just asks you to use separation of variables and to use Fourier series to find that function u of x and t. Okay, so let's go back to the board. Okay, so this is the problem I've already written over here on the left. You're wanting to solve the wave equation utt is equal to c squared uxx. You fix the string at either end, one at 0, at 0 and L. You have the initial velocity ut is equal to 0 at t is equal to 0, and then you have an initial displacement that looks like this. Okay, and if you wanted to figure out what these equations are, they're just linear equations. I didn't actually have to give you the initial condition in the question. I could have said, go and figure out what the initial condition has to be, and then you just figure out what are the lines that go through the midpoints. Okay, so how do you start this question? Well, you could start it from the very basic theory of doing the separation of variables, and I always say again and again that it's good for you to be able to do that if you wanted to. So you could go here, you set u to be a function of x times a function of t, you do all the separation, you find the separable solutions, you add them all up, you get the Fourier series, okay? But here, just because we want to push things forward, we're going to assume that you have your solution ready from either looking at the lecture notes and or just knowing it yourself. Okay, so this is problem set number 9, question 2. And so the solution that you know is that if you have this wave equation with the Dirichlet conditions, then the solution u of x and t is equal to an infinite sum. These are over sinusoidals. I think we called them sine of n pi x over L times, and then you have two time oscillations, a cosine in time and a sine in time, and you call one an times cosine. And the combination here is n pi ct over L plus bn times sine of n pi ct over L, like that. Okay, and I didn't reference here where this formula is from, but it's from, this is from theorem 16.3. So if you want to refer to this is theorem 16.3. Okay, and then now you impose the initial velocity condition. So ut of x and 0 is equal to 0. Okay, so you have to take a derivative of this cosine, and you get a sine, and then you take the derivative of the sine, you get a cosine in time. And then when you take the derivative of the cosine here, you get a sine, and then you set t is equal to 0, so that sine disappears, leaving you only with this term here. So from that, you would conclude that the bn's here have to be equal to 0. So this tells you that bn is equal to 0. And then finally, you need to impose the initial condition, u of x and 0. So you're going to stick in t is equal to 0 to that equation here, and you get u of x and 0, which is your desired function. Well, here we've already written this u of x and 0. I was going to write f of x is equal to the sum of the sinusoidals of n pi x over L. And then the cosine becomes a 1, and you're left with an an. So from that, you would conclude that the ans are just the it's just the Fourier sine series formula for the odd extension of the function. Okay, so you get that an is 2 over L, and then the integral from 0 to L of the initial condition times sine of n pi x over L dx. Okay? All right, and then now you're free to put this guy into there, and then just integrate. And that's where it gets a little bit messy. It's not as bad as, well, I always say that, don't I? I say it's not as bad as it looks, but I think that's quite relative. Sometimes you see what I write and you think, oh, that looks really bad. And then even after you do it, you might think, oh, that was really bad. But I actually don't think it's that bad. Okay, so now you have to put in the initial condition of x and 0, and you go back to the problem set, and it's told you what that initial condition is, and you have to split it between a segment when it's less than p, and then a segment when it's greater than p. Okay, so you're going to write your an as 2 over L. You have an integral that goes from 0 to p, and then you go to the problem set question. It's told you that its initial condition of hx over p. Just make sure, for instance, that if I put x equal to p, then I get h for the height, as you should. And then this is multiplied by sine of n pi x over L. And then you add that to a segment from p to L, like that. And then you have to put in the other portion of the initial condition. That's h times L minus x over L minus p. So again, make sure that if you put in x equal to p here, then both numerator and denominator cancel, and you're left with h, as you should get for the height of the string. And then this is a sine of n pi x over L dx. Okay? Okay, so, well, why do I say this? I mean, this looks pretty nasty, but it's not too bad, right? The first thing that you should just understand that it shouldn't intimidate you is that you've got L's all over the place. Sometimes you put the problem so that L is equal to pi, so a lot of these factors disappear, but they're just factors. Right? So it's just a bookkeeping thing. The next thing you should notice is that if I call this part of the integral, say, I1, and then this part of the integral, I2, that you can go and compute each one separately, and they're both going to require an integration by parts, right? Because you have a linear function here times a sinusoidal, so you'll let u be this linear function, or let u be this linear function. The other thing to notice is that this is just the integral of, for example, for the simple case where L is equal to pi, this is just something like x times sine x for this first one, and then the second one is something like a minus x times sine of nx. Okay, so even though it looks nasty, it's not so bad, because once you eliminate all the unnecessary factors, these are functions that you've already integrated in the past. Okay, let's do one of them together. Let's just do the simplest one, the I1 together. Again, just so you get a feel for how it works. So I'm going to let I1 be equal to 2 over L. I'll include this factor in the definition of I1, and then I'm going to factor out the h over p, like this. Okay. So when you do the integration by parts, you'll let u be equal to x, and dv equal to sine of n pi x over L. This is your dv. And your u will be that thing there. U will be equal to x. And you get u times v, so I have to integrate the sign. That gets me a negative. I have a u, which is x. I have the factor of n pi L times the cosine of n pi x over L. Okay, and then just make sure that if I take the derivative of this cosine of n pi x over L, you'll get the factors of L over n pi canceling with the factor of n pi over L, and then a negative sign, because that looks about right. And then this goes from 0 to p. And then you have to subtract du times v. Or in this case, you have to add, because you have the factor of 1 here. I have an L over n pi factor coming out 0 to p. And then the derivative of the x is 1. That gets you 1 times the cosine n pi x over L, like this. Okay, and then close your brackets. Okay, now unfortunately, usually a lot of these things disappear, right? Because when you set in the boundaries, a lot of these end up either being 0, 1s, or minus 1 to the ends, and so forth. Here, you're not so lucky. Okay, so you'll notice that you have a cosine of n pi p over L, and there's not much you can do with that. Okay, unless p takes a very special number. Similarly, on the left-hand side, you have a cosine of 0, but then this x here is equal to 0. So at least that left boundary condition will disappear. You still have to integrate this thing here, and you get a sine factor. So let's go ahead and set the boundary condition. We only have the top boundary condition there. So it's a 2h over L times p. And then you have the top boundary condition that's a minus pl over n pi times a cosine of n pi p over L. The 0 boundary disappears, and then you have to integrate this thing plus L over n pi, and then you have another factor of L over n pi times the sine of n pi x over L from 0 to p. Okay. Finally, when you stick in 0 into the sine function, it disappears, and you only have the p endpoint. Okay? So at the end of the day, you have something that doesn't look very nice. Right, that's part of the problem. So this is 2h over LP. This looks like a minus PL over n pi p over L. And then you get an L squared over n pi squared here. And then you get a sine of n pi p over L. Okay? And that's it. So you have this for I1. Doesn't look very nice, but actually when you go and compute I2, what you find is that this factor here, there's an associated negative of this factor here, so it goes away. And you're kind of left with only a combination of this sine of n pi p over L. Okay? I'm going to show you how you might do it with a computer instead of doing it by hand, using a program called Mathematica. But you can also do similar things with MATLAB using symbolic computing. So now I want to show you how you would do this using a computer. Okay, so this is a system called Mathematica. Actually, this is a, you would say that doing computations, doing mathematics on a computer, there are kind of two types of system. One is MATLAB. These are essentially using floating point numbers, and then this is a system where it uses exact computer algebra. So you can do things like integration and simplification. This is, in fact, the system that goes into Wolfram Alpha, if you know what Wolfram Alpha is. So there's a website where you can put a lot of these things into the website, and it'll give you answers. So behind the scenes, Wolfram Alpha is running. It's probably just running Mathematica. So I've put in the two integrals. I've asked to integrate the first one, and I've asked to integrate the second one, and I add them together. So you can see the typical output if you integrate the first one. This gives you the typical output, and that's what we just derived. You have a cosine component, and then you have a sine component together. This is the 2 over L times the initial condition times sine of n pi x over L, okay? And then if you integrate the second one, this is what you have. And so, as I warned you, the cosine sticks around. But when you add the two together, they will disappear. Here you have a sine of n pi factor, which you see pop up, and that needs to be manually set to 0. Either manually set to 0, or through some kind of explicit assumption, you have to tell the system that n here is an integer, so make sure you simplify this to be 0. So you add them to get together here. I1 plus I2, and then this is what the command is to make sure you simplify it, and then you assume that n is an integer. And that's the formula that you have, okay? So you'll notice that, okay, so it's a 2h L squared times a sinusoidal factor, n pi p over L. And you'll notice that there's a factor of p here on the bottom, and that was the factor of p that was missing in the solutions. So if I now go to the solutions here, you'll see the solutions are not very helpful. It doesn't give you the computations because they are just computations. It's the same procedure as usual, resulting in this, and there's a factor of p here missing at the bottom. Okay, let's have a look at what it looks like through MATLAB. Okay, here's the code to do it with MATLAB. It's the same code as we've always really worked with. You're going to set your physical constant, c, the length of the string L, the height is being raised at h, and the point that you'd like to pluck it at. So let's set it to be 0.5, which is the halfway point. And then you make a mesh in x, you make a mesh in t, and then you design your function. So these are the bn coefficients. This should really be called an coefficients. I'll correct it to an instead of bn here, so it's more consistent. And then this constructs the general term of the Fourier series, an times sine of n pi x over L times cosine of n pi ct over L. And then finally there's a loop, and in the loop you increment time, you increase time on each step of the loop, and at every moment in time you're going to form a Fourier series with n elements. Here n is equal to 50. So and as usual, this code will be uploaded on the website where you can run it yourselves. Let's run this and just see what it looks like. So this is a Plucked string with the midpoint at x equal to 0.5. That's what you see here. It's a string of length 1 from 0 to 1. And then now if I run the animation, you'll see that it does the thing that we observed before because we've done this version of the problem before. So the string deflects in that way. Okay. Okay, but what's new about this problem is that we can now change the location where it's being plucked at. That's a very good question. Someone's asked, what's missing in the model to make it look like a real string? That's an excellent question. Let's get to that in a minute. I want to play with p a little bit here, so I'm going to change the point where it's plucked at, and so let's change it to be 0.25. A quarter of the way through the string. Okay. And so now this is what it looks like here. Again, our string from 0 to 1 is being plucked at a height of 1, but now it's plucked a little bit more to the left of the string. And then you run this, you run it, and then this is what it looks like. Okay. Remember here that this is using Fourier series, so really, if you wanted to get these corners nice and crisp and sharp as they should be, then you have to increase the number of modes, but actually it is extremely slowly convergent. So even with a very high number of modes, it still won't look very crisp even to visual accuracy. And you know that it would never be crisp. It would never be sharp because they're just cosines and sines that are approximating it. And you have things like the Fourier convergence theory and the Gibbs phenomenon, which limit how sharp you can get. Okay. Now, so the question is, why does this look unnatural? Let me go back to the 0.5 case here. And it's an excellent question. Why does this look unnatural compared to what I might imagine for how a string looks? And I think there are two responses to that. The first is that this model here doesn't take into account, things like damping. Okay, so a real string, when you pluck it, it's initially going to damp. Damping is going to kick in, friction will kick in, the string will come to a rest. So you might say that what you're seeing here, these simulations are only valid as long as the damping is really, really weak, or that you're looking for very, very short initial times, right, when the damping is not going to kick in. And maybe your eyes and the way that, the way that we're able to observe motion, our natural limits, makes it so that these motions look unnatural, even though they might look natural initially in time. Okay? That's my first response to the question, that you're missing certain crucial things like damping. The other thing that you're missing is nonlinearity. So these equations that we've derived, you remember when we applied Newton's laws and all that, not only did they ignore damping, but they assumed that the deflections in the string are small, right? So we had to assume that the gradients in the string are small. And you might look at this picture and you say, well, what does it mean to have a small gradient? Is this what it means to have a small gradient? Is a gradient, which is essentially a gradient of h, is that really considered to be small? And that's, I think, one of the main reasons why this doesn't look as realistic as what you would hope. And what I can do is I can make it look more realistic simply by making this look like a longer string. So your model is valid essentially for long strings, or strings which are only weakly deflected. So instead, I can change the axis here to be, say, -5 to 5. Okay. And now you see we've not really changed anything. We've just kind of changed our perspective of the vertical scale. And you see that now it looks a lot longer and the gradient here looks a lot more shallow. Really, the right way of doing it, let me do it the right way rather than do it the wrong way. So I'm going to keep the limits to be from -1 to 1, but I'm going to decrease the h. So I'm going to take that to be, let's take it to be 0.2 instead of 1. So we're going to pluck the string now only to a height of 0.2. And then now this is more consistent, or at least it's apparently more consistent with the initial assumption we had that the string is only weakly deflected. Okay, and then now we're going to play the animation, and it's going really slow because we're going to play the animation. I like to make this go a little bit faster. So instead, I'm going to not take 100 steps like this. I'll only take 50 steps like this, and that should have the effect of making the animation a little bit faster. Okay, and then now I'm going to play the animation. And you might look at this picture at least further away and you say, oh, okay, now that looks a little bit more realistic. It looks sort of what I imagine for an oscillating string. Let's try it again for 0.25. And then we'll lower the h even further to be 0.1, and let's make it even faster. Take only fewer steps in time. Okay. Sorry, I wanted to change the location where I was plucking the string. Let's pluck it again a quarter of the way through the domain. So now it's being plucked a little bit closer to the left-hand side, quarter of the way through the domain. And then before, if you remember when we played the picture, it looked a bit funny. It didn't look like what you would expect. And maybe now it looks a little bit more realistic for what you would imagine for a string that's being plucked a quarter of the way through. Okay? So that's my response to you, that essentially you are missing certain critical ingredients in the problem. You're missing things like damping. But a lot of that is essentially because the model that you have is only for weakly deflected strings. A lot of the reason why it doesn't look as what you expect is for weakly deflected strings. If you look at it from a different perspective, from further away, now it looks a little bit more realistic for the small vibration of a string. Okay? Okay, so now let me go back to the board. That essentially caps off that problem set 9, question 2. And then now we get to move on to this second to last topic. Depends on whether you consider the math music to be a topic. Let's say the third to last topic, because the math music will be a topic. Okay, so as with all math courses, we only teach you a very thin slice of everything, right? There are waves on all kinds of geometries. We've only taught you for the string. And you might wonder, well, how do I do it for other geometries? How do I do it for a drum, right? How do I do it for a general shape? You might have a solid that you're interested in studying the vibrations on, and it would still, as long as those deflections are very small, it would still be governed by something very similar to a wave equation, perhaps even identical to the wave equation. Okay. Now, there are other phenomena that exhibit waves, right? And in particular, I want you to imagine a situation where, for example, you're standing here, and your friend is standing there, and you're both holding a string. You're holding the ends of a thin string, and you send in a wave. Okay? And so you're going to flick the string up and send your wave, and what you would expect is that the wave then propagates to your friend. Okay? And depending on how they're holding their end of the string, it might propagate back, it might reflect back, it might flip upside down and then reflect back that way. It might stay on top, right? So it depends on what the condition at the other side is. You might imagine other situations, like what if there is no person holding the string there? I just have a string which is momentarily in midair, and I flick it, and then what happens there? Okay. So these are slightly, they're at first sight quite similar to these problems here for finite strings. Actually, here the string might be, it is essentially finite in reality, right? So you would be able to apply the same techniques as before, but you want to consider the limit here that L tends to infinity, a infinite or a semi-infinite string. In particular, I want to study the problem of UTT is equal to c squared uxx. But now my domain is from minus infinity to infinity. Okay, so this is now a wave equation posed on a doubly infinite interval. Okay, and I'm also going to have an initial condition that I have to specify. So let's call that f of x. And I'm also going to have to specify an initial velocity for the string. Let's call that g of x. Okay. Okay, now because it's being posed on the infinite interval, you might also ask, do I need to worry about the boundary conditions at infinity? And the answer is no, you don't really need to worry about the boundary conditions at infinity as long as it's well behaved. And here, just for simplicity, let's think of the boundary. So we're going to say u tends to 0 as x tends to plus or minus 1. Okay. You can have other boundary conditions like u tends to a constant, but just for simplicity, let's consider u tends to 0. This can be weakened as well. And it's good for you to wonder, I'm going to change this, in fact. I'd rather not take that boundary condition just because it's not stated explicitly in the notes. I'm going to just say that the u is bounded at infinity. But you'll see in a moment, you'll see very quickly whether or not we actually need to specify necessary boundary conditions on u. Okay. So now, what we're going to do, this chapter is essentially divided into two pieces, really. The first piece is going to teach you a general solution of this problem, okay, without this initial condition and without the initial velocity condition, okay. The second result from that chapter is going to teach you about the particular solution, the particular general solution that encapsulates a initial condition f and initial velocity g. Okay. Okay. So I just want to refer to the exact numbering of the problems. So the first result looks like it's numbered theorem 18.1 in the notes. Okay. And the theorem tells you that every solution of the wave equation on a semi or a doubly infinite interval is equal to a superposition of a left traveling wave and a right traveling wave. So this is theorem 18.1. And it says that every solution of, I'll write on the next line here, UTP is equal to c squared uxx on the doubly infinite interval minus infinity to infinity is written as an f piece and a g piece, as it's written in the notes. And so u of xt is equal to capital F of x minus ct plus capital G of x plus ct. Okay. Okay. Now, this is a bit funny. You might never have seen this kind of formulation where you have an initial two independent variables, an x and a t, and they're combined in funny combinations, x minus ct, x plus ct. But then again, those of you who have taken courses on waves will see these combinations all over the place. This thing here is a left traveling wave. So this is a right traveling wave. And this here is a left traveling wave. And here I'm assuming that c is greater than 0 without loss. Both of these is c is greater than 0. Otherwise, your interpretation of which one's right traveling and which one's left traveling is going to switch. Okay? Let's show you an animation of this. Let's just plot a given function here. So f here is a generic function, and g is a generic function. Okay? So you get to pick whatever function you want to put in here, and as long as it satisfies this form, it is going to work. Okay? So let's look at a typical example of such a thing where we're going to make a little animation of this so you can see what's actually going on. Okay? I'm going to design a function. I'm going to design a function f of x here, and let's just take it to be an exponential, a Gaussian function, so minus x squared. Okay, and then I'm going to plot it. So just it looks like this, and I'm doing it with MATLAB just because it's, sorry, Mathematica just because it's a little bit faster. Okay, so there's our Gaussian function, okay? And the point here is that we want to consider what happens when you plot f of x minus ct instead of f of x, okay? So let's just take c to be equal to 1. And then we're going to plot f of x minus c times t, but we're going to do, I do an animation. Let's just do a manipulate command. Okay, so what this command says is essentially put in different values of t that range from 0 to 10. You'll get a little slider bar for you to do that. And then plot what this function looks like, f of x minus ct, and here it is. So when t increases, you see it's a right traveling wave. Okay? And the interpretation is if you change this to an x plus ct, it would be a left traveling wave. So let's just try it ourselves. Okay, and then if I move t forwards in time, and it moves towards the left or it moves towards the right. Okay, so different functions I could put in, for instance, let me put in sine of x squared, like this. And then I can move, let's change this to x minus ct, so it's right traveling. And then I can as well consider the right traveling motion of that, or consider the left traveling motion of that. You'll see that these little artifacts here where it doesn't quite look sinusoidal when you move it, that's just because of the accuracy of the plotting. Okay, that it's not sampling enough points as it does so. Okay, let's go back. Okay, so we've just firstly explained why you can interpret this as a right traveling wave and why you can interpret that as a left traveling wave. Okay. The other way to interpret it is just to study the function, right? suppose I were to give you this as the initial f of x function, okay? And let me take one feature of that graph and let me call that x naught. So at x naught, I have the maximum of the function, okay? Then a little bit later in time, you now have f of x naught, if I think of f of x minus ct, like this, and this maximum here, right, has shifted, okay? And you can see what the shift has to be here, that it's the value, this will be the value of this quantity of x minus ct, such that when you stick that combination in for a different value of t, you return to x naught. Okay? Okay, so if it's x minus ct, it moves towards the right. If it's x plus ct, it moves towards the left. And the way that you would prove this is basically to make a coordinate transformation of this combination of x minus ct. You're saying I'm going to make a new variable, and I'm going to call it c for this x minus ct. And then I'm going to make a new variable, and I'm going to call it eta for this x plus ct. And then you're going to transform the differential equation into those two new variables and then simplify it. And you're going to find out that if you do that, then it gets really simple. But you have to just go through a bunch of chain rules to do that proof. So I'm going to let this c be equal to x minus ct. Everyone struggles to make that Greek variable. You've never seen it before. And you're going to let eta be equal to x plus ct. Okay. If you've never seen it before, there's a difference between the c, which has more wiggles, or zeta, which has fewer wiggles. And there's lots of debates about whether you should pronounce it xi or chi. Okay? Or xi or something like that. And actually, I remember asking some students who took ancient Greek, and they had to say, oh, well, it depends on whether you're doing ancient Greek or modern Greek or whatnot. I like to call it xi. Okay. So you're going to make that coordinate transformation, and then you have to convert the differential equation. So you're going to let u of xt, this is the former solution of the differential equation, you're going to call that now a big U of c and eta. And you're going to now convert all the derivatives of your differential equation into c and eta. Okay? So let's first convert the x derivative. So d dx is now, you have to now differentiate. We're gonna do it absent from, we're gonna treat these as operators and not worry about putting in the u here. You could put in the u if you wanted to, but it doesn't do anything. So when you take the derivative of this with respect to x, you have to essentially differentiate through the c and the eta, because you have to remember here that this is a function of, this is c of x and y of, x and t, and this is a function of eta of x and t. So then you have to take a chain rule for both components. Okay. So you're going to write d dc here, and then you're going to write d d eta here, and then you just have to stick in the factors here that make sure that you end up with the x. So if I put this as d c d eta, d c dx, and this is d eta dx, then the way you check it basically just kind of cancel out those two factors, and you notice it gives you. Okay. And then d c dx here is just the partial derivative of c with respect to x. So that gives you a 1. This is a 1 times the d dc plus a 1 times the d d eta. So similarly, d eta dx, go here, take the x partial derivative, and you have a 1. Okay, and there you are. Okay, so now you're going to do the same thing with t. Let's do the same thing with t. d dt. Again, you have to differentiate through the two new variables, a ddc and dd eta. And then you have to put in the factors here that makes that gets you the ddt in the bottom. So if I take this to be dc dt, and if I take this to be d eta dt, then that gets me there. Okay? So now the dc dt is a minus c. This is a minus c times d dc. And then a d eta dt is a plus c. d d. Okay? Good. So you're halfway there. You now have to take the second derivatives because you have to convert the second order differential equation. Okay? So you have to do the chain rule again and obtain the double derivative with respect to x and then the double derivative with respect to t. Okay? I'm going to teach you a trick of how to do that so you can do it very quickly. Okay, the first thing is I'm going to stop writing this fractional notation, right? And it's just instead write the sub-index notation. So we've shown that dx like this is essentially dc plus d eta. Okay? So if you want to apply that formula, you just apply the operator. This is an operator. It operates on functions. You can just stick in your u here and stick in a big U here, and that gets you the conversion of the derivatives. And then we've also shown that this is basically a minus c dc plus d eta. And that's a minus d eta. I was pausing there because I was wondering whether I want to keep the sign in there or not, but let's just do it this way. Okay. If you want to get the double derivatives, you can essentially treat these as operators and then just stack the operators next to each other. So if I want dxx, I could stack these two together and I have a dc plus d eta and then dc plus d eta. So you can do algebra on operators in the same way that you just do algebra on your normal functions. Okay? And then now this is just a quadratic expansion you usually have. So the first one is the double derivative. The next one is the mixed derivative, so you have a c eta plus an eta c, right? But by equality of mixed partials, as long as the function is continuous and differentiable, you can swap the ordering, so that gets you a twice dc eta, and then you have a eta eta. Okay? If you did it the long route with the chain rule and everything, you get the same answer. Okay? Right. So the next thing is you have to take the two time derivatives. That's a tt here. And again, you just stack them next to each other. This is a minus c dc minus d eta. And then a minus c dc minus d eta. Okay, you get the c squared coming out. And then you have to expand the quadratic factors again. So this gets you c minus 2 c eta plus a eta eta. Okay, and then we're done. Okay. So now you go to your wave equation here, which is on the semi-infinite interval, and then you simply stick in these transformations that you have for the derivatives. Okay, so you have the dtt is equal to c squared times this factor here, where the operators are applied to the unknown function u. Okay, so we can hopefully memorize it. I'll erase it. Okay, so now I have utt is equal to c squared uxx, and then I swap in the double derivative for the operators that I've found, so that this gets me a c squared, and it gets me a dxc minus 2c eta plus eta eta times the big U, because now little u is big U once you've done the coordinate transformation. That's a c squared, and then you have the same thing here, except for the sign, plus 2c eta plus eta eta times the big U. Okay, and then go and expand all these operators, and you'll notice that everything will cancel. This cancels, and this cancels, and this cancels, and this cancels. The only thing that doesn't cancel is the mixed derivative. Okay, so you get the mixed derivative on the left, and you move it over to the right-hand side, and this gives you essentially 4 times the mixed derivative. dc eta of u is equal to 0. Okay? Okay, so now I'm going to take this thing and I'm just integrate it twice. Okay, so I integrate it the first time. So you integrate in eta, so this is basically, you can just cancel out the 4u if you like. But this now gives you du dc is a function of eta. Okay, I'm going to call this a temporary function. Let's call it g tilde of eta. I don't need to call it g a temporary function. No, I don't need it. I can call it. Sorry. This is an fc. I integrate in eta. And I get that. Of course. So, okay. So now, just make sure, if you did it right, take this thing here and take the derivative with respect to eta. This does not depend on eta, so you get 0, and you're left with the top line. Okay, and then now you just integrate this with respect to c. I did want to make this a temporary function for reasons that you'll see in a second. And then if I integrate in c, I'm going to have the integral of this function here plus an unknown function of eta. Okay, so just make sure you take this new line, take the derivative with respect to c. The g disappears, leaving us with purely a function of c. So f prime of c is f tilde. And then again, you can take the derivative with respect to eta and make sure you return up to the top line. So that is a solution of this equation where f and g are general functions. Right? So f and this is really quite crucial. F and g are just general functions. Okay. So any function that you want to put in here will work. As long as you put in f, so you design any function you like, an exponential or a sinusoidal, as long as you put in the combination of x minus ct into it, or x plus ct into it, then it will formally satisfy the wave equation. And so it's a solution of the wave equation. Obviously, it's not a solution for all the situations you can imagine, because there's usually an initial condition and an initial velocity, which will constrain the possible functions that you have. Okay, so we've gone about 10 minutes over time. Just want to summarize now what we've done. So we've looked at chapter 18. We've looked at how to solve the wave equation on an infinite interval. Okay, and as I said, chapter 18 is divided into 2 pieces. The first piece we've done here, we've essentially shown that every solution of this equation with no constraints on the initial condition or no constraints on the initial velocity can be written as a function of c and a function of eta, where c and eta are these 2 special combinations of a right traveling wave and a left traveling wave. Okay? The second part of it, which we'll do tomorrow, is how do you solve a particular problem where I've given you an initial displacement and an initial velocity. Okay? And that's basically it for chapter 18. It's those 2 elements, and at that point we'll be ready to finish up that second to last problem set. Okay. Otherwise, have a good rest of your Thursday, and I'll see some of you tomorrow.